Hello friends, welcome to the online lecture series. Today we will see another application of your differentiable equation, and the topic is simple electric circuit, in which the first series circuit is your LR. Is inductance, resistance which are connected in a series. In such a circuit, we have to find the what current is flowing in your LR circuit. For that, we require some basic terminology, the voltage across some components. We will start today's topic, simple electric circuit. The voltage drop across the resistance means how much voltage across your resistance can be calculated with the help of the multiplication of your resistance and the current which is flowing through that resistance, that is a IR. Again, the second component, that is my capacitor. What are the voltage across your capacitor, which can be given by Vc is equal to Q upon C, is the voltage across your capacitor. And third one, the voltage across your inductance. How to calculate is that the voltage across your inductance is L times di upon dt, which is gives the voltage across your inductance. So today we will see the first electric circuit, and that circuit is your LR circuit. Means your inductance and resistance which are connected in a series, and some voltage is applied to this circuit. When the voltage is applied to this circuit, the current is flowing through the given particular components, that is R and inductance. And we have to find the value of your I depends on the R and L which is connected in a series. Means how much ohm resistor is connected and how much inductance is connected in your that particular circuit. So according to your value of your R and L, the current is flowing in this circuit. We have to calculate that current with the help of the differentiable equation. So we already know the Kirchhoff voltage law, the voltage across the circuit. So here the R and your L and the voltage E are connected in the series. The current I is flowing to the given circuit. Then by Kirchhoff voltage law, we know that the voltage across your resistor is VR plus the voltage across your inductance, that is a VL. Your both summation is equal to the applied EMF according to the Kirchhoff voltage law. So we know that the value for VL is equal to L into di upon dt. So we have to replace the value of your voltages across inductance and resistance in this equation. So equation becomes L di upon dt plus Ri is equal to E. So there is a differentiable equation in I. So we have to convert this differentiable equation into linear differentiable equation. So we know that the linear differentiable equation in which the derivative terms whose coefficient should be 1. Here the L is get multiplied to di upon dt. So the entire differentiable equation is divided by L. So we get di upon dt plus R upon L I is equal to E upon L. The differentiable equation in I, that is in current. So we get this differentiable equation in I when we compare this differentiable equation in the general form of the differentiable equation dy by dx plus P of y is equal to Q. And we know that when the differentiable equation in the form of dy by dx plus P times y is equal to Q, its integrating factor is e raised to P, means e raised to integration of your P with respect to x variable. So when we compare this differentiable equation, the value of your y is I, value of your P is R upon L, and value of your Q is E upon L. So we say that the value for P is R upon L and the value for Q is E upon L. So integrating factor of this differentiable equation is E integration R upon L dt. R upon L is the constant because the resistance and inductance values are fixed in any electric circuit. So that becomes the constant. So constant outside your integration dt, the integration of your dt becomes t. So integrating factor is RT upon E. And we know that the general solution of such a differentiable equation can be calculated multiplying by the independent variable to integrating factor. So here general solution I into integrating factor is equal to integration of your right hand side, or we say that right hand side into integrating factor dt plus k, the constant of your integration. So replacing the value of your integrating factor, so we get I into e raised to RT upon L, and we know that the value of your that R right hand side is E upon L, which is constant and which is taken outside your integration. So we get a general solution of such a differentiable equation by integrating. So I e raised to RT upon L, E upon L remains as it is. The integration of your e raised to RT upon L is e raised to RT upon L, and the coefficient of its t is get divided by. So again this L get cancelled. We get the general solution of this differentiable equation. That is I e raised to RT upon L is equal to E upon R. L get cancelled. E raised to RT upon L plus k. To find the value of your constant of your integration, we have to use the initial condition. At t is equal to 0, means there is a k is equal to 0. Before that, we are just multiplying the e raised to minus RT upon L to the differentiable equation. So we get I is equal to E upon R plus k e raised to RT upon L, which is the current at any time. So applying initial condition, we have to find the value of this current. So we say that at t equal to 0, I equal to 0, then this solution becomes replacing the value of your current and value of your t 0, it becomes 0, and e raised to 0 is equal to 1. So we get 0 0 is equal to E upon R plus k, and this value of your k is minus times E upon R. The value of your k is minus E upon R. So putting the value of your k in this equation, value of your k is minus E upon R. We have to replace here, and we get a general solution, that is a current at any time t after just taking the common E upon R in this. So we say that there is a 1 minus this. So this is the current at any time t when we are applying the initial condition on this particular solution. This is the current at any time t by applying initial condition. We know that as time elapses, the current flowing through the given circuit is increases. So we say that as t tends to infinity, the value of your e raised to minus RT upon L is tending towards 0. It means the current reaches to its maximum value. So the maximum current which is flowing the circuit is given by I max is equal to E upon R. So E upon R is the maximum current which is flowing in a given circuit. So in this way, we can find the current flowing through in your LR circuit. This is the theoretical part of this electric circuit. We will see one simple example to understand the concept. The resistance 100 ohm and inductance 0.5 Henry are connected in a series with a battery of 20 volts. Find the current in the circuit as a function of T. Means we have to find the current which is in this circuit. So here in this circuit, the resistance of 100 ohm and the inductance value is 0.5 Henry, and your voltage is 20 volt, which is connected in a series. So according to the Kirchhoff Voltage Law, we said that VL plus VR is equal to E, and we know that the value for VL is equal to I times L times di upon dt, and value for VR is nothing but a value for Ri is equal to E. So dividing this entire differentiable equation by L, we get di upon dt dividing this differentiable equation by L, we get di upon dt R upon L, and E is equal to E upon L. So differentiable equation becomes di upon dt is equal to 200, I is equal to 40. A linear differentiable equation in I. When we compare this differentiable equation in the standard form of the differentiable equation dy by dx plus p times y is equal to q, so we get the value for p is equal to 200 and value for q is equal to, it is a 40, which is constant. Again, we have to find the integrating factor of this differentiable equation. So integrating factor of the differentiable equation is e raised to integration of your p times dt. So value for p is 200. So 200 is constant. So we have to just take the 200 outside your integration. So it becomes e raised to 200. It's my integrating factor. The general solution of the differentiable equation of I is I times integrating factor is equal to integration right hand side into integrating factor dt plus t. So the value of your I is I, value for your integrating factor, that is e raised to 200t, and our right hand side is 440, we have to replace here. Again, integrating factor is e raised to 200t. So integrating your right hand side with respect to t, so 40 is my constant, we have to just taken the 40 outside your integration. So it becomes this. An integration of your e raised to 200t up can be found with the help of the formula. The formula is this e raised to, because the 40 is not present, we have to just remove this e raised to ax into dx equal to e raised to ax upon. So the value of your a is 200, so it becomes this. Again 400 and 200, sorry, 40 and 200. We have to just make the simplification. So we get I e raised to 200t is equal to e raised to 200t upon 50 plus k. Okay. Then we have to use the initial condition at t is equal to 0, I equal to 0. So the value of your K is 1/50, and we have to replace the value of your K in your equation number A. So we get this equation A becomes I e raised to 200t 1/50 e raised to 200t minus 1/50. Again minus 1/50 and 1/50. From that we have to take common 1/50. So this is the equation of the current. And lastly, we have to just multiply the given equation by e raised to minus 200t. This is the current at any time t. In this way, we can find the current which is flowing through the electric circuit. Thank you. We will just see the next topic on next